Good morning, good afternoon, and good evening, everybody, and welcome to another episode of Loosely Coupled, brought to you by Bridging the Gap. My name is Cuddles Kronsky, and I'll be your host tonight. And I hope everybody has something nice to drink. I, as always, have some nice coffee in the jug, just to get through the evening. And today we're going to be looping. Going to be doing some fun loops, a little bit of a defense of a technical excellence, and through a very fun, clever tool, we'll be looking at how to defend technical excellence, and by showing the consequences of not doing quality work, but doing speed at the same time. So, to defend the technical excellence today, joining us live on stream is Chris Simon. Chris, welcome back to the stream.
Hi there, how's it going?
Pretty good, pretty good. Happy to have you here again. Yeah, a completely different topic for a change, right? Because last time we spoke about ubiquitous language, living language, and how to maintain it. We had a little bit of a dive into contextive. A lot of people got really interested to utilize contextive for various utilities, and now we're going to be talking about a completely different tool. Or visualizing the problem space with a completely different tool, and talking about quality versus speed versus whatever expectations management or business may have, right? Because that's pretty much a organizational problem rather than an actual technological problem or architectural problem, but it heavily influences our world of architecture as we know it. So, to start with, what's the background? Why do we need to defend technical excellence? Tell us.
Yeah, well, good question. Good way to start. So I guess, I can reflect on my personal journey on this topic and what led me to want to share this talk. And it was really living in a world where I just kept seeing over and over again the similar patterns, which is the most common one being, engineers saying, well, if we had more time, we would do X, but we have a deadline, and so we're not going to do that thing. Even though we know it's probably the right thing to do, but we'll come back and fix it up later. And obviously, as I'm sure everyone listening to this right now is probably either chuckling or crying to themselves, you never go back and fix it later. And I kept seeing this happening, and then not just that, but the consequences of that, the slowdowns, the inevitable, hitting issues where either people didn't understand what they had to do later, or we did understand what we had to do, but there was so much cleanup to be done before we could do it. And it just felt like it was a bit of a false economy, like this idea that we were trying to save on time and not actually getting there. So I got interested in this, and I guess over the years I discovered a whole bunch of different ideas, and they started to coalesce in my head, the connections between them. So one of them was the idea of systems thinking, coming from, I guess, the tradition of Donella Meadows' book, Thinking in Systems, a primer. Then I came across Peter Nauer's Programming as Theory Building, which is a wonderful article that explores the idea that one of the most important, well, the essential element of programming is actually developing the theory of the program in the heads of the software developers. And then I came across this idea from Martin Fowler, which explores the difference between internal and external quality. And I found myself wanting to understand the connection between these things, because I felt this instinct that there was a connection. And so, yeah, prepared this talk, delivered at a bunch of conferences now. I think tonight, I don't necessarily think we're not going to just run through the talk, because that's not as exciting if you just watch me sort of starting off. But I did, there's a link I can share to my website, which has a video of the talk from NDC London in January. And that's, I think, a pretty good recap of it if anyone wants to watch that. But what we're going to do tonight is I'm just going to show a couple of key slides from the talk, and then we're going to dive into, as you said, visualization. Because what I realized as I sort of came to build this model in my head of what was going on and why these, things were happening, I found myself wanting to be able to, for myself, but also help other people make the argument, make a better argument for why it's not a good idea to skip these things. What I didn't do in the talk is, really dig into some of what are the alternatives, because there always is a deadline. So what do you do about that? And maybe tonight we can go into that as well a bit later. So I guess just to, explain a bit more of that background. Do you want to show up the screen share? I don't know if that's live yet.
Yeah, sure. Let's switch it.
So these are some slides from the talk, and I kind of I started exploring a couple of stories. Like imagine your product owner comes along, says I got a new idea for a feature. You put it on your backlog. The dev team comes along, starts building. QA comes along, finds a bug, and you get told, no, we haven't got time to fix it, so we're just going to ship it to production, and the bug goes into production. And another similar journey, except this time the team says, no, we want to do some design work. We need to do maybe some domain modeling, event storming. Get told, no, we haven't got time. We're a rocket ship. So they go to production, but because of the lack of design thinking, we end up with a bit of a mess in the corner of the program. And then this last one is a key one, because it explores what happens when this happens again. The team doesn't bother doing design because they know they're not going to get given permission to do it, but hit that mess. And so that causes some slowdowns and delays, and then probably more likelihood of getting bugs. And so then we go to production with a bigger mess and a bug. And this is actually the heart of the idea that we're going to explore today, because what that story I just told is actually a feedback loop in action. And so this is coming from the systems thinking tradition, is looking at feedback loops, and that's one of the key ideas in this talk and what we're going to be talking about tonight. The other key idea is this idea of an intuition pump. This is from a guy called Daniel Dennett, who's a philosopher. And this is a really important thing here, because as we get into looking at these feedback loops, there's a temptation to sort of take them a bit too seriously sometimes. And the best way to interpret them is that they're a modeling tool. They're a way of exploring your own thought processes. They're a way of explaining yourself to people. Like a persuasion machine, as he puts it. The idea that we're trying to help people think about what's going on in these very complex socio-technical systems that we're dealing with, because you can't come up with an accurate model of human behavior precisely, and you can't come up with an exact model of organizational behavior. So this is more of a way of illustrating your perception, your perspective, and hopefully doing it in such a way that you can sort of make the case of what you believe to be true.
Given the audience, at least the common members of the audience that pop by here from time to time during the live streams, a lot of us already know that all models are wrong, but some of them are useful.
Exactly. That's a key idea here. And so, the idea of an intuition pump is interesting as well, because I think we can also look at, the reasons we're told that we haven't got time is also a form of intuition pump, because it's not really based on evidence. There's an intuition to it, though, and it's often expressed as this iron triangle. The idea that we've got like scope, cost, and schedule, and this was actually the original formulation here. The quality of the work is constrained by the project's budget, deadline, and scope. You can trade off between things. So if you want more scope, you want more features, you need more time or more money. If you want to spend less, well, you need to take longer, or you need to have a reduced scope. So all these things, but they're constraints by quality. This was the original formulation. If you don't trade off, then quality will suffer. I thought this was really interesting, because this was from 1968. Dr. Martin Barnes, he created the idea of this iron triangle, which I discovered later is actually in some places in the world called the golden triangle. I don't know if you've come across that. No. I've mostly heard of it as the iron triangle. But interestingly, the reason I find this fascinating is because, in my experience, quality has become one of the things that people want to trade off. They don't treat it as the thing that you have to hold still and you trade off around it. They say, no, quality is a trade-off. Usually the thing that has to be held still is like the schedule, and so the time gets held still, and quality is negotiable. And I think that, as we're going to explore tonight, my belief is that that's a mistake. Interestingly, then in 1969, so just 1 year later, he did actually put quality on the edge of the triangle. And I wish I could ask him why he did that. Maybe it made sense in civil engineering, which is the field he was in, but I don't think it makes sense for software. There's another kind of idea here, which is the good, fast, cheap concepts. We talk about the iron triangle sometimes in this, good, fast, cheap, pick two. And this is one where I think engineers often find this quite appealing, actually. It's used as a defense against unrealistic expectations, where people say, surely,
Guilty.
just you can
Guilty as
deliver,
charged.
you can deliver, a clone of Facebook in a week with an intern, right? Like, how can, and a core code subscription? Why haven't you, why haven't you done it yet? And you're like, well, you can have it good, fast, or cheap. Pick two, but if you want it, you got to increase it. So I found this iron triangle used in both ways. Like sometimes it was, we can't move the deadline, so you got to cut quality. And sometimes it was engineers saying, "Look, we can't deliver that much scope, so you're going to have to either spend more money or reduce the scope or whatever." And there's as you said, like there's an intuition to this, and I think it is not unreasonable for a certain set of problems. And so we should
but
trust
not
intuition.
all problems, not all problems
Exactly,
per se.
exactly. And this is where, so here's some references to thinking in systems. But I'm just going to skip through this because where this comes in software is this idea of internal and external quality. And so I think that this is from Martin Fowler. The idea that external quality is user experience or scope fixing functionality, but internal quality is the design issues, coupling, low cohesion, poor abstractions, what's often called technical debt. I have a real objection to that term sometimes. Like, it's kind of valid in one sense because it evokes this metaphor of ever increasing debt. Like you have a loan and you pay interest on it and you get more interest every time, because if you don't pay down the debt, the loan value keeps increasing. So you pay more and more interest every time. And that's valid. That's another feedback loop in action, actually, as we'll see. But I don't like it because I think it disguises just bad engineering. I think technical debt, as it was originally intended by Ward Cunningham, was supposed to represent what you learn along the way. He never advocated for cutting corners, but he did advocate getting started before you fully understand what you're doing. So there's a difference between saying we don't understand the problem very well right now. We may not understand how to use the technology that we have to use, but we're going to get started so we can learn as we go. And then once you learn, you're supposed to put what you've learned into practice. And he described that as paying down technical debt. But I think over time, people have sort of abused this term technical debt and said it's for any time we cut corners or any time we don't do the right thing. And I think Ward was very clear that his idea wasn't about cutting corners. It wasn't about doing the wrong thing when you know what the right thing is. It was get started before you know what the right thing is and learn what the right thing is by doing, and then pay down the technical debt with what you've learned.
That's interesting, because I never heard about that approach towards defining what technical debt is.
Yeah.
Literally, for the whole of my career, the only definition for technical debt is that I heard was we cut corners, so now this is technical debt.
Yeah.
Or it's too old, it's so old and written so long ago that now it became technical debt or technological debt because now it's completely outdated.
And I get it why people have done this, because the metaphor is so appealing, right? The interest repayment concept is so appealing. But I think it's a shame that this subtle nuance of Ward's original vision has been lost. This idea that it's not about cutting corners, it's about learning by doing. And so technical debt is the gap between what we did and what we would have done if we had known then what we know now. It's a bit of a mouthful, but you can imagine if you go back in time with all the knowledge you've acquired through doing the projects, how would you build it? And if you look at the difference between what you did build and what you would have built if you could go back in time and do it again, that's technical debt. That's the gap. Everything else, we knew the right thing to do, but we just didn't do it because we didn't think we had enough time. I think that the better term for that is cruft, because that is just the idea of like accumulating cruft. It's because you don't do housekeeping. You just let the dirt pile up, and it's this idea of just crud and cruft accumulating due to lack of care and maintenance and care and attention.
I had just the perfect example, and it's not even the debt is not even the result of anything technology. It's purely the result of organizational mismanagement and putting the wrong people to the right task.
Yeah.
You're fairly aware that I'm an integration architect, so I deal with integration platforms of the sorts. And at this one company, I was tasked with, okay, let's fix the integration platform because there are problems. turns out they put former DBAs to the task of building an integration platform. What could go wrong? Of course, everything went wrong because they built an MDM system instead of an integration platform, covered around with Azure functions to feed it data and extract data out of it. And they accumulated so much cruft over the years, over fixing delivery data models and doing operations, that basically that team was swamped with operations and became the bottleneck for every project, because over 60% of the time that they had was committed to operational work. And this is that result of craft. They didn't do housekeeping, and they didn't do housekeeping because they didn't know better.
Yeah.
From their perspective, they were doing what they were asked for.
I might disagree with you a little bit on the terminology there, because that actually could be an interesting case where technical debt is the right term, because it's about the fact that they didn't know. They had to learn as they were going. But it's not like they knew what to do better and decided not to do it. They genuinely didn't know.
Well, at a certain point where that knowledge arrived at the team, they were so defensively dug in their positions that they disregarded that they may be wrong about things.
Fair enough. Yeah.
So this is a psychology and organizational psychology problem rather than a technological problem or architectural problem, but it resulted in the same result of having a lot of technical debt with craft, which basically created a bottleneck.
Yeah, absolutely. Yeah, well, it's interesting. So there's a lot of things going on there. Obviously, there's psychological factors as well. But I think the interesting thing, the common thread there is, once it gets worse, the fact that it's bad makes it get worse faster, right? It just keeps declining at an ever increasing rate. And that's the fundamental part of the systems thinking that we're going to bring into this. So I think actually now might be a good time to, we've been talking about this for a little bit now. Let's dig into this Loopy tool, because this is what we've been sort of building up to. Yeah. This tool that helps you visualize and explain what's going on in your systems. So
now, for those interested, unfortunately, from the perspective of the studio, I cannot post on LinkedIn, so I'm going to do that in a moment. But I'm posting the comment on YouTube. So here are the links. And I'm going to add Loopy as a QR code on the screen in a moment, so you can play around with it. Yeah. All right. So those who want to play around, it's there. Please do.
Yeah, you can follow along
there. And here's the QR code for those who can scan the QR.
Yeah, I will say I have had some people try and use this on their phones. It does technically work, but it's not a great experience. I think if you can get on a laptop or a tablet, you'll have a better time.
I mean, just scan the QR and just WhatsApp to yourself or something like that, or email yourself the link just to make it quicker.
Yeah, cool. So getting back to this, so the way this works, so this tool is great. It was it's an open source tool. I did not build it. I just stumbled across it and found it really helpful. You are looking at this canvas, right? And so you can start to draw up a diagram, and then you can run a simulation of what the diagram is telling you. So the key elements of what we call a causal loop diagram are nodes that model different quantities. So I'm going to start by modeling a very simple real-world concept, and then we'll start translating into technical concepts. So let's imagine we're modeling the population of rabbits in the world. So we're going to say here, sorry, I see there's some comments coming from people. Yeah, I think I agree with what Maxim is saying. I haven't got a chance to read it properly, but very much the role of leadership in this. And hopefully what we're doing now might be a tool that people can use to help convince their leadership of the kind of role that they need to play. But getting back into the causal loop diagram, so you start with a quantity, right? And so if we simulate a single quantity, it's not very exciting. We can increase the quantity and decrease the quantity. This is us sort of provoking the model, but it doesn't really tell us much yet because it's just one thing. So what we want to look at is what's the relationship between different quantities that we're interested in. So let's do another one, which is maybe the population of baby rabbits, because we're looking for, and it's in the name, causal loops, we're looking for cause and effect relationships. So if I draw a line from here to here, what I'm saying is that the number of baby rabbits, if it goes up, then eventually the number of rabbits will go up. This equal sign represents the fact that any change on one side is reflected onto the other side with a delay, but in the same direction. So if I increase the quantity of baby rabbits, eventually we'll have an increased population of rabbits. If I decrease the population of baby rabbits, eventually we'll have a decreased population of rabbits. This is a really important point, that it's both directions. It's not necessarily always positive or negative. It's just about being in the same direction. Sometimes you'll see in this simple mode, they use a plus sign. I tend not to use the plus sign because I think that makes people think always only of increasing quantities. And so I prefer to use the equal sign that represents the fact that it's the same change. Where it starts to get very more interesting is when we introduce the loop concept. So we've got the causal part, cause and effect, baby rabbits to rabbits.
Yeah.
The loop part is when we bring it back in the other direction, because as we know, if you've got more rabbits, you're going to have more baby rabbits. So now we've created a feedback loop. And if we increase the number of baby rabbits, we're going to increase the number of rabbits, which is going to increase the number of baby rabbits, which is going to increase the number of rabbits, and so on. And this kind of feedback loop, where once you sort of initiate a change in a given direction, that change will continue and accelerate, is called a reinforcing feedback loop. So if we do the other direction, though, like if we say, well, maybe there's some illness which causes not enough baby rabbits to be born, well, eventually the population could decline and die out. And both of these cases, whether it's increasing to the maximum or decreasing to nothing, is an example of a reinforcing feedback loop. So that's one key concept. Reinforcing feedback loops created by two links at a minimum that have the same kind of change in both directions. There's another kind of loop we can do, which is a balancing feedback loop. So let's just say we've got a quantity which represents the amount of grass. In this case, if we have more grass, we're going to have more rabbits. But if we have more rabbits, well, they're going to eat the grass. So actually, that's going to be an opposing link. So instead of an equal sign, we have this symbol that says if rabbits goes up, grass is going to go down. And this is where things get quite interesting, because now what we'll see is we get more rabbits, but now the sign drops. It flips here. And so you can see here now, instead of growing to full capacity or instead of declining away to nothing, it actually becomes very stable. We have this, it's in balance. When something pushes too far in one direction, the cause and effect causes something else to happen, which brings it back. And so if you model this over time, you actually see it sort of, this kind of wave effect goes up and down and up and down, and it wobbles around a very stable kind of point. So there's so many examples in the real world that we can see where this pattern is playing out. So we've alluded to some of them already. The reinforcing feedback loop is like a savings account, where you get some interest, or a loan account, like technical debt metaphor says, where you pay interest. Either way, once you have interest, then you have a bigger principal, well, not principal necessarily, but a bigger amount of money, which either means you're going to earn more interest on the next cycle, or you're going to be paying more interest on the next cycle.
If you don't pay your mortgage or something, loan.
Exactly. You don't pay the interest or pay the repayments. So those are both reinforcing feedback loops. Whatever starts happening happens more and more and more over time. That's a reinforcing feedback loop. Whereas now we have this balancing feedback loop. So a great example of that is like the thermostat in your house. You set it to the temperature that you want. It tries heating up the house, and then eventually the house gets to the temperature. And so there's a feedback loop that senses the temperature and stops the heating. And then the heat is sort of lost out into the outside world, which causes the temperature to go down again, and that crosses a threshold, which reactivates the heating. And you see this kind of wobble around the set point that you want is an example of a balancing feedback loop. Now that one's actually quite complex, because you've got all the energy and things are going in different directions, and you've got discontinuities because you've got the heater being turned on and off rather than a smooth cycle. But it is another example of a balancing feedback loop in action, where the goal is sustainable and predictable, and
it's balancing within the state of temperature, but not exactly balancing within the energy, because then that energy is basically gone, right?
That's right. That's right. The energy is lost. So you could model that as well and see what would happen, from an energy perspective. And actually, there are some interesting reinforcing feedback loops with energy. For example, like a refrigerator cools
Hmm.
what's inside, but it adds heat on the outside through the way that the refrigerator works, and so that can actually um, everyone using air conditioners in the hot summer can actually increase the need for air conditioning because of the heat generated by the energy consumption. So there's like, all these sorts of, this is the kind of things you start to spot once you learn more about systems thinking. You start to think about cause and effect, more than just one link of cause and effect. You think about the knock-on effects, what happens after that, and does it feed back in? And if it does feed back in, what does that mean for longer-term trends? Is it going to be getting worse or better, or stable? And
Chris,
so, yeah.
but now I need to ask, because we had Woody Zool previously
Mhm.
on the stream talking about identifying problems through looking at symptoms as
Mm,
signals rather than the
mm,
problems that we solve. And we had Hien Verschaatse uh,
mhm,
talking about what was that, decision making, I believe,
mm, mm,
the art of the decision making. Uh, the and from that, the core aspect is that causality is not always visible purely, because the effect we're seeing and the immediate thing that causes that is not exactly often the problem, right?
mm.
It's a chain of causality. So
Exactly.
how can we dive into and use Loopy to actually start uncovering and modeling that chain of causality? Because that's always the interesting part,
It
that
absolutely
wondering.
is. Yeah. And this is actually what I find this tool really valuable for, because what you do is you start with a very simple model, like a naive
Hmm.
model, and
Yeah.
you look at it and say, well, does this actually predict what I think is happening? As Woody said, you're looking at signals, and then you look at your model and say, is this giving me the same signals? And if it's not, that's a trigger to say, well, what am I missing here? There's so many things that you can be missing. You might be missing you might be focusing on the proximate cause and not the root cause. And there's various
Hmm.
techniques like 5 whys and things to try and follow a chain. You might be mixing up cause and effect. We see that a
Hmm.
lot. Correlation does not equal causation. Maybe you thought one thing was causing the other, but actually it was the other way around, and the second thing was causing the first thing. Or maybe they were both being caused by an independent third thing that you haven't identified yet. So this is what I find helpful here, is that it's not that it gives you these answers, but it
Hmm.
helps you see where the gap in your thinking is, because you can, when you test the model and you go, hang on, that's not what I'm seeing, that doesn't align with the signals that I'm observing, it sparks this sort of creative exploration of, well, what's the model not got that it needs to have? What else is involved here? And you start thinking, what else affects these quantities? What else have I got the directions all the right way around? And it can actually help you sort of reason through what's there. It's, as I said before, it's not a prediction engine. It's not a
Hmm.
simulation, an accurate
It's a
simulation,
model.
but it's a model. But I find, because you can visualize what's happening, you can see these things flipping around. I find it personally quite helpful for sparking that creative journey of trying to find what else is going on. So this actually might be a good time to bring up some other loops that here's some I
You
prepared
bring up
earlier.
loops, and I have a
Yeah.
visitor again
Oh,
in
cool.
the camera. He's a 5 months old puppy, and he just needs hugs all of a sudden. So
Mhm.
he just jumped in and gave me some kisses. Okay,
Oh,
stopped.
very nice.
He's a lovely big guy, but still very very much a kiddo at heart.
Mhm. Well, he's anytime he wants to jump up, he's very welcome.
Obviously, it's the second time he's making an appearance live. So,
Yeah.
all right, yeah.
So this is an example of, like a starting point, right? You might say, okay, what's
Yeah,
actually going on when we're writing software? Um,
that's the naive model.
Naive model,
Let's say.
yeah. So I was trying to explore, like, what actually happens with cruft in our systems, and I thought, well, here's what I know. I know that we get new requirements, and so we build new software. And whenever we build new software, hopefully we're delivering new value. but also we're probably creating cruft along the way, or technical debt, depending on the
Likely.
situation. Yeah, like it's pretty rare that you get to not do that at all. And so you can look at this and say, well, this doesn't seem to line up with what I experience. Like, this seems to imply that, you know, I could just keep adding new things and it would just be very simple. Every time I get new software, new value, and new craft, but the craft sits on the side and doesn't really affect anything. And I'm like, well, that doesn't seem right. The craft does affect things. Okay, obviously I know it does. So how does it affect things? So we go back and we say, okay, what else is going on here? And maybe we think, well, what's going on is the craft is affecting things because maybe if we were to spend time refactoring the craft, that would take away from the time spent adding value. So we end up with a kind of a feedback loop here, a balancing feedback loop, actually, because what we're saying is, if we spend time adding value, then we get craft. If we spend time refactoring the craft, then we spend time adding the value. But if we spend time adding the value, if we're spending less time adding value, we're probably spending less time adding craft. So this is a really interesting one, because I found myself staring at this for ages trying to make sense of it, because I'm like, it didn't align with my intuition, because I was thinking, but hang on, it's really just the nature of this cause and effect. Like, do I actually get less craft just because I'm adding, I'm spending less time adding value? So actually, it might make more sense to say the very first version of this that I created, I actually just had craft there. And I was like, hang on, if I spend time adding value and that adds craft, and I spend some time refactoring, yeah, I guess that does reduce the craft eventually, but it's actually more of a direct link, maybe reducing the craft. And so I found myself going, hang on, what? Like, this is the thought process I go through as I'm building these things. Like, what does this mean? Does this reflect what I'm seeing? Is this the right relationship? And the insight that I had here looking at this is that most of these quantities are actually rates of change. And so craft is an absolute. So that's why I changed it to new craft. And this is a really important point, actually. Like, if you are building causal loops, make sure that everything is in the same kind of order. You know what I mean? Like first or second order. So first order is like distance, second order is like velocity, third order like acceleration. You can't necessarily have a simple connection between two nodes where one of them is like an absolute value, like the total amount of craft in your system, and the other is like a velocity, which is the change. So I started focusing more on velocity, like new requirements, time spent in an iteration adding value, new crafts. So it's not so much about the total amount of craft, but how much new craft are we adding to the system is one way of interpreting it. And this is really subtle, and it can be hard to identify this and to explain it. But as you build up these diagrams and sort of see what happens, it sort of does help you reason through what's going on. So this is, I think, we've talked about a whole bunch of different concepts here. We talked about reinforcing loops and balancing loops. We talked about cause and effect. And I think this is another really important point as you get into more advanced diagramming, is to reflect on, are we talking about things that are in the same type of effects, like speed versus distance, or change over, like, are we talking about, like, maybe story points per sprint? You can't then connect that to total amount of code in the system. You could connect it to new code in the sprint, but not total amount of code, because the accumulation effect doesn't happen here. Does that make sense?
It's like when I'm diagramming, which basically means not using visual things like Loopy, but basically diagramming. I always have like Jackie Reed in the back of my head, and whenever I'm discussing certain things, live diagramming with somebody, for example, with Philip, with whom we design a lot of content, we often put too many abstraction layers in one diagram. And we know in the back of both of us, we both know Jackie, we both know what she would say about this diagram. She would basically scold us for putting too many abstraction layers on a one diagram. And this is, I think, the equivalent, what you're talking about, the velocity versus absolute, is basically the diagram equivalent of abstractions on one model, right? And basically, if we're thinking about value of change versus absolutes, this is exactly that aspect there.
So one of the things you can do, so there is a mechanism with the causal loop you can use to sort of try and deal with this, and we can see it in action here. If we have new requirements, we spend time adding value. Because we're adding value, we're not adding new craft. But I introduced the concept of confusion, and instead of time refactoring, time making sense of things. So I was kind of interested in my mind, like, what's the, how much time are we, like, even if we're not doing the refactoring,
Right.
what impact is the craft having? And the fact is there's new crafts, we have more confusion, more time making sense of things. But more than that, I introduced this new kind of link here, which is what's called an F+ link. And so we've seen before the equals and the opposing. So this one is an equal one, this is opposing. And F+ represents, it's like a gate, only a positive signal can come through. So I said before that you can't do an accumulator. That was kind of like, well, you can't do an accumulator with what I've shown you so far. But now I'm showing you there is another thing you can do that actually does create an accumulation effect. So when there's more craft, we're going to get more confusion. But just because we might go a sprint without adding new craft, it doesn't decrease the amount of confusion. So you get the positive impact, but not the negative impact. And that's why the loop stopped. You notice all the other loops just kept going forever, because both the positive signals and the negative signals were reflected and echoed through the loop. But this one, once it goes through once, the positive signal is allowed through, which increases confusion. But then we spend some time making sense of things. We spend less time adding craft. That doesn't decrease the confusion.
Right.
Adding less craft in a given cycle doesn't decrease the confusion. You actually have to reduce the craft to reduce the confusion. So
but then now, is that connection between time making sense of things and time adding value actually a true connection?
Well, I think there's some validity there. Like, time is a zero-sum game. You've only got so much time in a week, right? So if you're spending more time making sense of things, you're spending less time adding value. If you're spending less time making sense of things, you spend more time adding value. Hopefully, I mean, it's a valid question, and this is exactly the kind of questions that I hope that these kind of diagrams provoke. My hope is that when people look at this, think, oh, I'm going to give this a go. It's not that you just sort of, I mean, you might spend some time just doing it on your own and testing your brain and going, does this make sense? Is this what I see? But more valuable, I think, is to get it in front of a group of people, like bring it to your team and say, I did this. Is this what's happening here? What do you guys think? Does this link make sense? Is there something else going on here? And as you see, we keep building this diagram up, right? Like, we keep adding more things. And this is where it gets to the point where I think there's a point of validity here, which is, I said, well, actually, as confusion increases, we increase the craft. So that's the feedback loop, right? So now we've got two feedback loops, a balancing loop and a reinforcing loop. And so now we have the positive effect of the confusion. And the positive effect of the confusion creates more craft, which creates more confusion. So what's happening here is that we might get periods of time where we're not adding as much craft as we previously were, but our confusion rapidly maxes out. Because
that's basically the principle of cognitive load in anywhere.
Yeah, and in particular, this idea of the reinforcement. So this is like your interest payments on your technical debt, is that just the more you have, the more you're going to be paying. The more you're paying, the more debt you owe, the more it's going to cost you, and it just accelerates over time. And this is the thing I think a lot of people miss with technical debt. They think it's like this linear connection. If we estimate it would take a week in this cycle. Sorry, let's say we estimate it would take 1 day in this cycle, and we haven't got a day, so we'll skip it, and we will just make up that day later. But the problem is that if you try and make it up later, it's not just 1 day; it becomes 2 days. And then if you try and make it up 3 months later, it actually becomes 3 days. You try and make it up 6 months later, it's become 2 weeks, because of this compounding interest effect, this reinforcing feedback. And this is what we're trying to visualize here with this diagram.
Yeah. For the people who joined late, if you want to ever look those up yourselves and play around with Loopy on Chris's examples, you can always go to the website, Defensive Technical Excellence, Chris's website. The slides are embedded in that site, so you can actually get the links for every single one of those loopies that we're looking at and play around with them.
Yeah, you can change it, add things, remove things, and see what happens. So
hold on. Loopies are great in one aspect, because all of this diagram is actually saved in the URL. So there is no disk space, nothing. You just you just pass everything as a URL. So basically, you save a string and you can recreate all of this easily through that.
It's pretty handy. I did spend some time. They do have a feature down here, like you can export a JSON file. But I found it a bit frustrating. I actually found myself really tempted to go and build like a VS Code extension, so you could like work on files and things. But I
that would be cool. Yeah,
that would be cool. But at the moment, what I found is the easiest thing is to just like save the link somewhere. So I keep these links in like my logseq personal data management, and then obviously in my slide decks for talks and things. But yeah, click the link and you can just put this link in a Slack message to someone and they can load it up and see exactly what you've been working on. But it's not like, I mean, this is not a very advanced tool in the sense of it's not like a shared, it's like Miro where you can be modeling on the same surface or something. It's really focused on just doing the simulation. But this diagram we're looking here, this is the granddaddy. So this is where I ended up with after like adding a whole bunch of stuff like bugs and craft and confusion. And when I give the talk, I don't go into as much explanation of these diagrams as I have done with you just now. I just sort of talk through the basics because I've only got a limited amount of time. But when I get to this diagram and people start seeing the arrows floating everywhere, and then the next thing, you can actually speed it up so we can go like what happens. And this sort of gives you a sense of like over the long term what's going on. And you know, I basically say, well, so because we're dealing with craft and we're not dealing with it, or we're accumulating craft and we're not dealing with it, we're accumulating bugs and we're not fixing them, or maybe we're fixing some bugs but not others, then we end up with this like maxed out confusion and no time to deliver any value to our customers at all. And everyone just looks at this diagram and goes, oh yes, absolutely, you make perfect sense. And it's like, that's that's what you're looking for, right? Like you want to show this to your manager and say, this is why we slow down over time. This is the problem. We're stuck in this mode where this feedback loops between confusion and craft and bugs just sort of like explodes over time through these reinforcing loops. And it doesn't matter really like how much new requirements you add, we're never going to get more value out of the system because these reinforcing feedback loops are overpowering any other kind of balance loops going on in the system.
Yeah, the system is constrained basically.
Yeah, but once again, like I said, this is not reality. This is not a simulation. This is a storytelling device, you know. So yeah, I want to convince you we should spend some time dealing with our craft, and this is the mechanism I'm going to use to convince you of it. But I think it's a pretty compelling one because it's got the animations and it just kind of develops, like I said, that intuition, so you can start to see what's going on.
Yeah, a picture says a lot more. 1,000 words, they say. This kind of a visual animated example says even more than 1,000, right?
Yeah, exactly. And I do think it has that effect. And at least that's the feedback I've been getting as I've been giving this talk, is people have been saying, oh yeah, it sort of really clicked for me. Another thing that I sort of try and connect it back to this iron triangle is to say, you know, part of the problem here is that the iron triangle presupposes a linear relationship between these quantities. And by looking at the feedback loops and understanding feedback loops now, what we can see is that there's a non-linear relationship. Because of the feedback loop, it's not like a simple trade-off. Like I said, it's not just 1 week now or 1 day now for 1 day later. It's 1 day now for a week later or 3 weeks later because of the feedback loop. So when we see that there's actually a feedback loop here between these trade-off quantities, you can't do like just a linear trade-off between them. That sort of helps you see that actually maybe external quantity, it's valid, you know, that distinction between scope and bugs, scope and features, maybe usability issues, sure, but internal quality, the things that actually affect our ability to interact with the code and to change the code, that's where we have to sort of keep it apart. And I mentioned this article, Peter Nauer, Programming is Theory Building. This is the thing that made me lean on confusion as a central quantity in those diagrams. You might decide, if you're building your own diagrams, to focus on other things, like maybe confusion is not the central element that you want to focus on. But I chose to do that because I really like this model, this Programming is Theory Building, and I think it's kind of my effort to include what he's saying here into the models. So if people haven't come across this before, what he's saying is the main claim of theory building view of programming is an essential part of any program. The theory of it is something that cannot be conceivably expressed, but is bound to human beings. So he's talking about how the team that has built the code has developed in their minds a shared understanding of how the code works, and that's the theory of the code. And without that, you're lost. So he goes on to describe the death of a program. It's when the programmer team possessing the theory is dissolved. I find this quite evocative. A dead program may continue to be used for execution in a computer and to produce useful results. The state of death becomes visible when demands for modifications of the program cannot be intelligently answered. So in other words, we need to change something and everyone goes, I don't know how to do it. That's a dead program in Peter Nau's view. So revival of a program is the rebuilding of its theory by a new programmer team. So I kind of decided that the way I was going to model it is that confusion is kind of like an absence of the theory of the system. The more cruft that we have, the more bugs that we're dealing with, the more confused the team is. That's like the inverse of having a theory. If you're confused by the system, you don't have a theory of the system. If you have a theory of the system, you're less confused by it. And this was why I chose to model confusion in the causal loops.
When I use confusion, it's usually attributed to a quote from Don Norman.
Okay.
That's the design of everyday things. That's a very user experience book, but it kind of resonates with what I do as an integration architect as well, because Don Norman states that complexity is inherent. It's not about making things simple, because you cannot make them simpler at times. It's confusion that's the bad part, not complexity itself. So, but confusion stems from poorly managed complexity. And if we do well-managed complexity, then we avoid confusion. And that's one of the key aspects that I'm teaching when teaching integration architecture, is that if you do not manage interactions complexity between disparate systems, then of course you end up with confusion, because you build up that cognitive load that people need to understand who is communicating with who and via what means, and that complexity basically kills. Well, that confusion stemming from unmanaged complexity kills throughput.
Yeah,
it's exactly pretty much the same model.
Yeah, and I find I'm glad you brought that up, because this is something I've been sort of noodling around in my mind for a while now, which is that I think there's a lot of things that people assume are qualities of the system that actually are qualities of the relationship between the team and the system. So you're saying that confusion is caused by sort of unmanaged complexity. But you also gave a great example before of like the team that was asked to build an integration platform, but didn't necessarily have the skills or knowledge of how to do so. And I've worked in environments where, there was a team who had been maintaining a system for a really long time. They knew it inside and out. And then new people would join the team and they would come and say, oh, the system's so complex. And then you talk to the people that had been maintaining it for a long time and they would say, it's not complex at all. It's very simple. I know what's going on. And like, you've seen this, right? Like, I'm sure you've seen this.
Yeah.
So a lot of what many of us do, like those of us who are educators in this space, we're trying to help people build systems that are more understandable. And I think there's two elements to that. One is they're genuinely less complex, but the other is they follow conventions and patterns that are more prevalent in the industry, so that when people come into the system, they see something that is familiar to them and they can more readily understand it. So there's a combination of, is this easy to understand as an absolute fact of the system? And the other is this easy to understand for me, given what I've learned so far? And, this is like, we're obviously both part of the DDD community. And a lot of people found DDD to be really complex. And then a lot of other people found DDD to be like the savior that simplifies their systems. And both are true, right? Because it's not a property of the system itself. It's a property of what people are bringing to the system, their own ability to it and their experience.
It's actually a cognitive bias.
Yeah.
It's a cognitive bias called the curse of knowledge. So, especially as an educator, I experience this quite a lot. That's why I often implement feedback loops on my materials and go to other people, ask, is it clear, is it understandable, etc., just to show that some parts of my content and spar on those. Because I'm a subject to the curse of knowledge bias, which means that I omit certain things in my explanations because I deem them obvious.
Yep.
and easy because I have extensive knowledge on the subject. But from a perspective of a different person that doesn't have my knowledge, they're actually quite complex and not understandable. For me, that's basically with expertise. That's a moving bar. You constantly move it up because 2 years ago, certain things that I now talk about and are obvious to me weren't so obvious. I was researching them. Now they're obvious. It's like, yeah, that's obvious, but no, it wasn't. No, it's not for a lot of people. So it's a matter of asking yourself where that starting point is, and same with bringing people into the team to work on a specific domain system. It's the same problem. The amount of cognitive load over time increases to onboard somebody into that system. So for those people that stayed there for years, that's easy. But for those that just joined, the amount of cognitive load is not distributed over those years. It's actually condensed into a few months.
100%. And this is why we get the, I think Einar Host is a great guy from Norway who speaks about this. He's what he's called slash and burn development, which is, people join a company and they say, oh, this is too complex, we need to rebuild it. And then they slash it all down, burn it down, rebuild it, and then move on to the next company. And someone else comes in and goes, oh, this is too complex. The last people were terrible. You need to rebuild it.
Yeah.
Endless cycle of slashing and burning. And remaking it in the way that makes sense to us, even though it made sense to the last people, but it doesn't make sense to us because as you said, we didn't distribute the accumulation of knowledge over 2 or 3 years. We were expected to absorb it in a week, and it's just too difficult.
Yeah, and now I'm trying to recall where is that from, and I'm struggling. But there's
as a reference to some sort of farming practices in early humans.
Yeah, but not that one. That the thought that came into my head was about building systems.
Right.
Every complex system derived from a simple system.
Well,
Trying to do the other way around is ludicrous.
It's more than that. It's every complex system that works.
That's one.
A simple system that worked. You can't go straight to a complex system that works. You can build a complex system that doesn't work. You can do that straight away.
That's exactly the quote that was in my head. Yeah, that's that one. Yeah. So then that cognitive load of designing that system, building that system, making it work, is then stretched over years. That's why we avoid that confusion aspect and the cognitive load of learning it. But then if you come in later to the game and start working on that system, the cognitive load is humongous, and that's very, very problematic. That's why slash and burn is basically how a lot of people do. And the funny thing is, in Polish that would be an equivalent of a construction man, physical worker building things, or electrician coming to you, and a handyman fixing things, and it's just coming to the house and saying, who screwed it up for you this badly? Then redoing everything, and the next one coming up, and who screwed it up for you that badly?
Well, and this is right. And there was an era where I think that was the case, but what fixed that is over time standardization. Building, there's building codes and there's standard approaches, and so now a plumber that comes into your house, they're going to find the same size washers that they've got in their truck, same size pipes that they've got in their truck. They're going to follow this, like country standards. Like in Australia, we have Australian standards and international standards that say, well, it has to be this many meters from a bend or from a wall or from a door or whatever, and this is what's led to actually creating some sensible activity in that space, because people now can kind of come into a new environment and sort of know what to expect. We have nothing like that in technology, right? Like nothing in software development, at least. And we're trying. When you think about it, DDD is kind of trying to do that. So saying you should build your system out of these structures that follow conventional patterns like aggregates and value objects and domain services. You should extract your infrastructure concerns behind interfaces, which kind of follows ports and adapter pattern or something like that. You should divide your system into bounded contexts that represent sort of discrete areas of business domain or subdomain or functional areas or whatever you want to sort of base it on.
should we like pull Barry O'Reilly here into the call? Because
Maybe.
that's basically up his alleyway in terms of
Absolutely.
philosophy of architecture.
And actually, it's funny you mentioned that, because so in this talk, after sort of getting to this point where I've sort of demonstrated all of the feedback loops and like why it's such a problem, and then introduce Peter now to say like confusion is the key thing, I start to go into like, well, what things can we do to help us build a theory of the system that can help us, maintain the theory of the system over time. And this is where I start to talk about specific practices. So like domain modeling, event storming is something. So, and I think about event storming as something that we should do when we're starting a new thing, but also regularly. We should periodically, once a month, get everyone together and just do an event storm, just to keep the knowledge fresh. And new joiners come in and they learn so much so quickly through the knowledge sharing, that kind of thing.
It all stems from that aspect of having architecture iterative. Your business process is iterative, because model drift is a real thing. I mean, if you go to any of Barry's talks about residuality, exactly, he talks about model drift. Basically, if we model something, it already drifted away. The business already is doing something else. We're just approximating for what they were doing at this point. And that's always the problem, that this needs to be iterative. There's no other way around it. Same with residuality theory. It needs to be iterative. You need to iteratively find those residues, which is what Barry is always saying in that sense, right?
He's also saying you should do more of it in advance.
Yes.
Like you do need to, because what he's saying is like a little bit of simulation, in advance, like not a massive big waterfall thing, but a bit of simulation, random simulation of stress, can lead you to a structure that will be more evolvable over time. That's the premise. So I wanted to get to this slide because you mentioned Barry, and I was like, hey, I've got a picture of Barry just coming up. And actually, I'm doing a talk at DDD Europe this year with Andrea Magnorski, which is a reporting on some case studies of using residuality theory with some clients over the last 6 months, and I'm really excited to share those stories. And actually, there's a couple of elements to which this is relevant for what we're talking about here. So one of them is, I don't know if everyone's familiar with residuality theory, but just to briefly explain it, is this idea that we need to change the way we think about architecture. It's not a static structure. It's something that evolves over time. And the concept of a residue is the change in the architecture over time in reaction to a stressor. And the stressor is symbolized by the lightning bolt here. So we have a system, we get a lightning bolt stressor, we change the architecture, and that's a residue. And then what Barry says is, well, we can actually simulate these stresses and conceive of the residues in advance so we can prepare for them. We can design our system with the right abstractions and the right sort of extension points so that the residues that we've predicted will be easy to add. And the key thing that makes it work is this phenomenon of what Barry calls mathematical leverage, which is that if you do a random enough simulation of a large enough number of stresses, what you'll find is that they converge onto a smaller set of what he calls attractors, which leads to a smaller number of possible residues that will protect you from a large number of possible stresses. And so we can see here, like of the first 4 stresses, 2 of them led to the same residue, and the next 2 led to a different residue. So even though we analyzed 4 stresses, we only found 2 different residues. That's the key. And this is like what we've always done in a way. We just called it finding a good abstraction, but we didn't really know why it was a good abstraction. And now with residuality, we can look at a list of 100 stresses and say it's a good abstraction because it protects us from 50 stresses. And that's a really cool thing, I think. And
I need to grab Barry this year at DDD Europe, and because Barry has a background in integration architecture, and I need to have a chat with him over how to apply residuality theory for integration platforms and integration architecture, because I think there might be somewhere there that actually integration platforms can be, it's not always true, but can be a very strong residue, and that's my gut feeling on the matter.
Well, it's interesting you say that, because I actually caught up with Barry the other day as part of preparing this talk to sort of sense check how we were going with the case studies and things. And it's been really interesting, because actually putting residuality into practice has helped me understand it a bit more deeply, as you would imagine. Like it's a theory, and
Hmm.
then you do it, and then you sort of build an understanding of it. And I think when I went into it, I was kind of thinking about it as just a technique for designing an architecture, and now I think about it actually as a technique for just building knowledge generally. So epistemological philosophy in a way, and and so this is actually the other lens in which this is interesting. Barry talks about, he brings philosophy into his work. He talks about the concept of a Deleuzian walk, the idea of like you have to walk around an idea many times, look at it from different angles to kind of understand it. And so each of these stresses, and each time we think about a stressor and a different stressor and come up with a residue, is another Deleuzian walk around the possible design for the system.
Yeah.
And so I think actually the reason I bring that up in the context of the causal loop diagrams is that every time you create a causal loop diagram, that's another Deleuzian walk. You're
Ah.
taking a walk around the system to explore it and look at it from a different perspective. And that's connected to what I keep saying, which is that it's not an accurate representation. I think a far better description of it is a Deleuzian walk around the problem that you're exploring. You might explore it from other perspectives as well, take more walks around the problem. But a causal loop analysis is a really good Deleuzian walk from my perspective as well. And so that's what I mean. Like you can use this idea, like in a way, we were kind of using residuality before. We were looking at a model and then we were stressing the model. We said, but that doesn't explain this. And then we came up with a residue, which was a change to the model, which was to add another node or connect it in a different way. So we think about residuality as being the process of building up the model by stressing it, by saying, this doesn't make sense. There's still something that I can't see here. Doesn't explain X or whatever stresses. And then we came up with these residues for it. So yeah, it's a really interesting idea. And I do think it's a valuable technique. And I think that teams that start to apply it will like reduce the confusion in their teams. I think they'll see that the teams now understand why certain architectural decisions were made. They'll see the list of stresses and say, oh, I can see why we've put this abstraction here, because this is the possibilities, and we see that they converge on these residues as protecting from a large range of possibilities. And I think that's going to be really helpful for teams.
For a lot of them, yes, but I believe that unfortunately for a lot of companies, this requires quite a bit of maturity to get into this going forward,
Potentially.
to understand how important these kind of things are for
Yeah.
them to maintain validity of their IT systems.
Yeah, that's true. But also, I think that this is something that can be done in a very lightweight way. It can be something that you just can do yourself. You don't have to wait until your company says, like, yes, we're going to do residuality. You can just start keeping a list of stresses for yourself. And, you can use this process to not only help you design a future state of the system, but also to help build a more comprehensive understanding of the current system. So if you're joining a new team and you say, oh, do you want to try residuality? And they say, no, we haven't got time. Just do it yourself. Start building a list of stresses in a Google sheet, and you join the team and you say, oh, what's our system look like? And then you give you a diagram and you, okay, that's the system. And then you find out, actually, that's not the system because nobody updated the diagram the last time they changed something. And so that's a stressor. And then you go, okay, well, what's the residue? Now, what have I learned? There's actually this cache that's not on the diagram, or there's a database that's not on the diagram, or there's an integration platform that's not on the diagram. That's a
Yeah,
residue. And you build up a more comprehensive perspective of the system that way as well. And then you can start using it to design, well, where would we take it into the future as well? So I think you're right to an extent. Like, I think companies, it's going to take a while for more companies to start recognizing that they need to do this. I mean, if you think about event storming, Alberto came up with that in 2013. And 13 years later, we're still looking at, I would say, probably like maybe less than 5% of software teams are doing event storming. Like, that's crazy.
yeah.
Like, I would guarantee you 100% of software teams would benefit from doing event storming, and only 5% of them are. I'm just pulling these numbers out of thin air, but you know what I mean? So it could be decades before residuality is like widely adopted. But,
That's
that's
very
nice.
true.
Being part of our community is that you get access to these techniques before everyone else.
Yeah, that's the rock hard benefit of it.
Yeah.
But then just going back to something simpler, I strongly believe that a lot of the problems with causality and the undiscovered feedback loops and the things that are happening and the confusion that is there is because we're actually, a lot of the times, we're doing implicit architecture. We're not doing architecture per se. We're doing
Yeah.
implicit by building. And that's I think that's a very specific sin of companies focusing on a digital product. Because we need to be tactical, because we need to move fast, we need to deliver fast, we need to deliver that external quality. And that often, it's not only about cutting corners, it's about just building without designing, without properly looking at architecture beforehand.
So this is actually this is a good segue into another thing that I wanted to mention. This is not something I'd go into in this talk generally, and as I reflect on it, I wish that I had. But it's like, okay, so I'm telling you not to cut corners. I'm telling you to write tests, to do design work, to do TDD, whatever you think is going to improve the quality of the system and improve reduce confusion in the team. But how do you still deliver value when you've still got deadlines? Like, even once people are convinced that, okay, I can see how doing all this stuff is going to lead to a more balanced and resilient and stable and sustainable and predictable rate of change over time, that sounds great, but I still have a deadline. And I know that if I try and do some of these things, that yes, they might smooth out delivery rates over time, but they're going to slow me down right now. What am I supposed to do with that? And I think that's a very reasonable question. And I do have an answer for it, even though I didn't go into it in the talk. And the answer is based around a technique that I really find valuable called user story mapping from Jeff Patton. And the idea of this technique is that you orient each cycle of delivery not around a particular layer in the system or even a particular feature, but about the end-to-end experience required by a subset of your users. So what I mean by that is like, okay, so we've got a deadline, we need to get something live. The pushback that I often give to people is, and actually, who's going to use it on that date? Could we maybe say, okay, so our dream is that we get 100,000 users. Could we just pick 500 of them and let them use it on the first day? And if we made sure all those 500 people were just in one city, or they all have the same demographic requirements, or maybe it's just one company, then we can reduce the scope in a sensible way. We can reduce the scope down to a true MVP, which is minimum and viable. MVP's got such a dirty word in the sector now because so many people have done really bad MVPs. They've either made them non-minimal or they've made them minimum but not viable. And actually, that's not an MVP. An MVP should be minimum and viable. And for me, what minimum means is it's not about the size of the system. It's about the number of customers that you're building it for. And if you can build your system that's just for one customer, that will be the minimum amount of functionality you need to deliver. And that's the key, in my experience, to delivering the right quality on time and then giving yourself room to expand. Because I guarantee you, this is something that a lot of technical people do not take seriously enough, is that missing a deadline is disastrous for trust. And so I have a mantra when I'm writing software with leading a team or whatever, is never miss a deadline, but also don't necessarily always deliver what they thought they were going to get. So I would rather go live with something that has had a whole bunch of scope cut out of it at the last minute, but guaranteed go live on that date and get some trust that actually something's going to be there, and say to people, look, it's live now. It's only suitable for like 1% of the customer base, but let's get it in front of that 1%. And then you get feedback from those customers and you get trust built that you can actually deliver something. And then in the next cycle, you expand it to 3% of the customer base, and the next cycle 5%, and so on. You build on top of it. I've done this over and over again, and it works a treat. But you have to not miss the deadline. You have to go live on the day you said you were going to. But
so
also
that's
not
basically
actually deliver everything you thought you were going to deliver.
But that's what you're talking about is basically canary deployment elevated to requirements management and expectation management.
Product management and expectation management, all of that stuff. It all comes together, right? And so much of it is about collaboration between engineering and product leaders, and making sure that you're on the same page about what the priorities are here. And the reason I really like user story mapping is that you start with like the skeleton of your system from the start of the user journey to the end. And so event storming can help you build up like what this map looks like. And then you say, okay, if we were only going to build it for this particular customer and not the other customers, what would need to happen in each slice of the journey? And it turns out there's always a whole bunch of stuff that you can say, well, this customer needs this element, but it doesn't need this other feature. And that's how you decide what's in and out of scope for each cycle of the release. that is really, really helpful. I mean, you're right. It's expectation management, it's requirements management, it's product management, but it's product management done through the lens of understanding the technical consequences of it. Because so often when product leaders make a unilateral decision, this is the feature set and it must be live on this date, that's what puts the engineers in the position of saying, we have to cut corners because we cannot possibly meet that date. But when it's a collaborative decision that's made through both understanding the technical consequences and with pressure on trying to keep it as small as possible, that's the key to delivering something quickly, getting in front of customers, and allowing you to not cut the corners, because you can actually deliver just the thing you need to deliver at high quality, which is how you keep the predictable delivery through the rest of the projects, and allows you to continue to expand the feature set and get it out in front of more customers.
Yeah. The problem is that this puts a lot more effort on those who make the decisions about the scope, to actually analyze what are the features, what is the subset of requirements that would be viable for that particular time.
Understand your customers. You actually have to talk to your customers and understand what they value. You have to understand what's the thing that they really care about. And when you're looking at this thing and you're saying, well, should we put this in or should we put it out of the first release? And I always ask the question, if it wasn't in there, would they still buy it? And if the answer is, yeah, they probably would still pay for it, I'm like, well, it's out. You know, that's the litmus test. Because so often you're like, oh, we need to add it in because maybe they'll need it later, or this other person wants it. And there's so much rework avoidance theory going on where people are like, well, we're going to have to do it later, so we might as well do it now because it'll be more efficient. It's like, it's never more efficient to do something now that you only maybe need later. It adds complexity. It takes time away from like delivering high quality work now. So this is all like, you know, this is my philosophy of software development.
It's basically balancing that iron triangle all the time, right?
Yeah.
Scope versus cost versus time, governing a specific quality.
With a key observation of awareness of the feedback loops that are going to kick in if you make a bad choice there. Yeah.
Yeah, that awareness helps navigate that balancing act, because it's basically a balancing act.
Exactly.
Chris.
Yes.
An idea. Should we do something like domain storytelling only with Loopy? I'm serious. In that sense, it's not domain storytelling per se, but let's maybe emulate some completely random things. I'll be your SME and you'll be modeling.
You're talking about something where you describe a situation and I model it the way that you would do with domain storytelling. Absolutely. Just for clarity for people, I don't think causal loops could replace domain storytelling. I think domain storytelling.
No. Absolutely, they will not replace.
In it, you know, it looks kind of similar, like you got diagrams and loops and things, but it's more about flow of information, whereas causal loop about cause and effects of trends and things, so slightly different. But yes.
Yeah, that was just my mental model of different tools, especially DDD tools. The domain storytelling was the closest thing to what I had in mind in terms of doing that collaborative modeling.
Yeah, so I think that's a good idea.
I'll switch back to sharing.
Yeah, well, just before we get into that, I was just going to show you one last diagram from my bed ones, which is this. This is like the big one, which is what happens if you introduce, say, test-driven development and collaborative design with event storming, and the idea is that they affect the confusion with a balancing loop. So you got these reinforcing loops from craft and bugs, but you got balancing loops from these things, and so if you increase it, you can see confusion doesn't match that. It actually sort of, sometimes it gets larger, but then it gets lower because, you know, the impact of these practices. And this is kind of trying to visualize this whole mantra I've been saying, is like these practices of technical excellence that reduce confusion in the team are what allows you to sort of deliver new value steadily over time. And I'm not saying it's like static and fixed and it's always going to be perfect, but it's just not going to go and get stuck. You know, it's like, it's going to be this kind of like wave around the median is kind of the idea. But this took a long time to build this diagram, and it did. And, you know, I'm not saying like you get this immediately. You know, it took a lot of like playing around and trying to understand, like, how do I actually think about the relationship between these practices and confusion and all sorts of things. But it was fun. So, but I think that what you're asking for is a good idea. So let's put this one aside for now. I'll open up a new tab, and we'll what do you want to model?
Okay. Let's say, well,
You're on the hot seat now.
my forte is integration platforms, and I already joked to Vlad Kononov that his book basically kills 50% of my work because he described 50% of what I do. Can we model a behavior of, confusion stemming from coupling, for example?
Yeah, we could do that. So
from my perspective, coupling is in integration architecture, coupling is something that happens between distinct systems. Of course, there's coupling within systems, and the smaller the distance, according to Vlad Kononov, and the tighter the coupling on a low distance, that's actually cohesion, which is good. The problem with coupling on a high distance is if there is a lot of knowledge required between two distinct nodes to be able to function together, right? So we already have two nodes in that sense. We have two systems, and I think the aspect that is crucial that creates coupling, heightens the coupling, is the amount of knowledge. And then, of course, volatility, because distance will be a fixed value, right? So if I take Vlad's model,
right? So distance, as I understand it from Vlad's work, talking to him about it, distance is not a physical property of two systems. It's the perceived distance, right? So
perceived distance, yes.
It could be like if the two systems are owned by the same team, that's, even though one of them's in Paris and the other's in San Francisco, that's a low distance.
But that's
that are owned by a team that is on different time zones. That's a bigger distance because of the lack of knowledge sharing and the information.
But that's a socio-technical aspect of coupling, which is a bit of a different flavor of distance. The distance that Vlad usually goes into is from individual classes of code, then going to packages, namespaces, libraries, services, and then systems. So the size of the thing we're talking about, and the distance between classes is fairly small. The distance between individual, let's say, packages and namespaces is a little bit more, and then distance between two distinct, disparate domain systems is a lot larger than between classes, right?
Yeah, so that's all true. The reason I sort of jump straight to talking about teams, though, is because that's true, but not necessarily true, right? So you can make choices in terms of how you structure your code that can lead to, because this concept of perceived distance is critical, right? And so to give you a more concrete example of what I mean, the tooling that you use to interact with the code can affect the perceived distance. So let's say you've got an IDE that allows you to like click on a class and take you immediately to everywhere that class is used, reduces the perceived distance, even though it's in another namespace or another package, or maybe even in another repository. So this is what I mean by, even though I understand why Vlad uses those examples, I think that this concept of perceived distance is critical because it's actually what leads to it. And we need to think about, it's not just a static property of the code. It's like, how do we engage with the code? What tooling are we using? And coming back to that point we pulled before, is like, how familiar is the team with the code? Because if someone knows already that this code is depended on by a class that's in another namespace, that perceived distance is smaller than if they didn't know that already.
Yes, but that's dealing with cognitive load and the problem stemming from wrong organizing in a good or bad way how we work with that code. Where coupling perceived from an architectural perspective derives either from design or from operations. So as far as I would love to go deep diving into the socio-technical aspects of code and working with different aspects of code, we're gonna end up ending this session somewhere around 8 a.m. tomorrow. So just to simplify it,
It's true. Sorry, I'm going to be really annoying because I want to just add one more thing to that point about coupling, because you referenced Barry a few times now, particularly the model drift software attractors talk, and I think that's really quite relevant to this because in that talk he actually makes quite a bold claim, which is that coupling is an illusion that can only be perceived in hindsight once you have experienced the actual changes in the complex environment that occur. So what I mean by that is that you may design a system and you may look at it and say, this system is super loosely coupled, everything's fine. And then along comes a change that you never expected, and that change causes a like a proliferation of like change contagion across the whole system. And suddenly you go, actually, this is really tightly coupled. I didn't realize. And this is what Vlad calls volatility, right?
Yes.
The probability of change. And I think the distinction between Vlad and Barry's work is that Vlad says, okay, volatility is really important. And Barry says, yeah, it's important, but you can't predict it. So don't even try. And actually, what Barry says is that every system that we look at and say this is loosely coupled, we only say that because it has survived the changes that happened to occur to it, not because it was actually any sort of magical property.
Yeah, there may come a stressor that will showcase how tightly coupled it is.
Yes,
of course.
And this is in Vlad's world, that's volatility, but Barry's concept is we can't predict the volatility. But I think what Vlad adds that Barry doesn't always talk about, which is a shame, is these properties like distance and knowledge flow that I think are really critical as well. So I'm actually a big fan of trying to merge both of their thinking about this.
That's a difficult task to do. So for the sake of simplifying our model, let's not go into Barry, because that's gonna dive into so many aspects of different things that we could model, especially with socio-technical aspects and the unpredictability of volatility of things, etc. But what Vlad says is basically we're basing certain things from observation of the ecosystem, so things that were that we can then model into things that are. So for the sake of the of this modeling, let's leave distance out of it, because as an architect, as an integration architect, I'm working purely on a system-to-system distance. I'm never working on a distance of individual classes in that sense. Although if I go to an integration platform, and most integration platforms nowadays are microservice systems, so technically I'm working also on the service-to-service distance of coupling. But okay, let's say we're dealing with distinct systems. We're having coupling, and we have either volatility or shared knowledge. Now, the shared knowledge can be, if it's from what Vlad explains, if a system needs to know a lot about the other system, that's probably somewhere in the area of intrusive coupling, which is pathological, which means that we have a problem that's a very tight coupling. If a system needs to know very little about another system to actually make it work, to make that communication interaction happen, that's loosely coupled by design, by observation. And of course, it is somewhat of an illusion because we don't know all the stressors. I agree, but at least from the perspective of design and potentially later consequences of that design in operational coupling. So that's I believe that's functional coupling in Vlad's model. That's a looser type of coupling by design, not immune to anything, but somewhat safer, creating that residue. To an extent, we can control a little bit through our thinking process, modeling process, that we create more residues or less, but that's pretty much it. So the regular problem with coupling that people tend to have is because a lot of people don't know what integration architecture is. They don't know a lot of the times that there is something more than a REST endpoint. So a lot of communication with a lot of my clients at times is point to point. And the point-to-point is fine where you're a small startup and you have maybe 5 systems, because then it's manageable and it doesn't create confusion. But the more the systems you have, the more confusion you have, because the tighter the coupling is between the consumers of an API and the provider of the API. So we have potentially multiple consumers of one API, and there's coupling there, right? And then you have consequences of coupling there.
Yeah.
Perhaps I should send you the loopy that I already have for this. That would be a starting point, and we can modify that. What do you think?
Yeah, potentially. I mean, we can have a look at it. I think the one thing I was going to make an observation of is that you said we have 2 systems, so we have 2 nodes. In the context of building like a loopy diagram, I wouldn't necessarily start with thinking about the nodes in the system. Causal diagrams tend to. I think this is a really good one actually, because you're focusing on
causal.
Well, it is causal, but it's not a loop.
Not a loop.
There's causal effects here. So if we play, so you have a business change that causes a data model change, which causes a contract change, which causes the different consumers to change, which creates development work, which causes testing, which causes deployment activity. So this is definitely a causal diagram. So there's a lot of cause and effect. What there isn't is a feedback loop. So what you don't see here is, does any of this stuff actually cause any of this as well? And in a naive sense, it doesn't. But I think if we go back to this one, we start to see like a simple case where we do see that. And we could make the case that if you have shared knowledge, well, that increases coupling. And if you have volatility, that increases coupling. Do you think that if you have a more coupled system, that's going to, over time, lead to increasing the amount of shared knowledge? I think you could argue that it does, because once you have a coupled system, it becomes harder to change. And so when new changes come along, you're going to be more likely going to have to introduce more shared knowledge to accommodate that change, because it's easier to do it that way than it is to break the integration and reshape it in a way that's more loosely coupled. And so
I would say that the coupling probably creates confusion and cognitive load, and that then creates the need for more shared knowledge.
Yeah.
Or potentially also creates volatility.
Yeah. So let's say cognitive load, or let's just because it's kind of the same thing, we'll just treat it as confusion. So the coupling leads to confusion. Confusion leads to more shared knowledge, and confusion leads to more volatility, because confusion might mean that we end up changing both sides of the integration even though we didn't need to, which increases volatility. Or it might mean that the only way we can solve the problem is to introduce more shared knowledge, because otherwise, like, we haven't got the capacity right now to like recreate the integration in a more loosely coupled way to reduce the amount of shared knowledge, because that usually means having to like relocate functionality from one side of the integration to the other, which is often politically impossible because they're sometimes owned by completely different teams or whatever. So what this then shows us is a feedback loop, which is going to highlight that if we have even a slight increase in volatility, the confusion is going to feed back through the loop. I'll speed this up, and is gradually going to lead to increased coupling and increased confusion over time. So this is the kind of situation where the feedback loops become really valuable, because they stop us from just thinking what's happening right now, and they guide us to start thinking, well,
what will happen,
going to cause to happen in the future. And so I think with this diagram that you've created, I think it's a really good visualization of the immediate consequences of a change. When you want to start thinking in feedback loops, you want to start thinking, what are the longer term consequences? Does any of this activity increase the probability of more business changes in the future? Probably not, but it might increase the probability of data model changes, or contract changes maybe. So it depends. I'm not sure in like what you were thinking about with this, but that's what I'm always looking for, is these like, can I bring this back in? Is there a cause and effect back to the start? And that is where we start to see feedback loops. And then you might start to think, but is there anything that balances this? What kind of things happen that balance this? And so it might be, I don't know, maybe you have some sort of integration testing, or maybe, like you said, you often introduce an integration platform. And so maybe the integration platform we have to think here about like what would the quantity be that is the same kind of quantity, like just the presence of a platform is not there, but maybe
So the premise for a lot of ponderings, and when I explain complexity of of interactions between systems, is that is Tesla's law,
right.
the law of conversion of complexity. So it's not a matter of adding or removing complexity, because a specific problem domain has an inherent amount of complexity that cannot be reduced. It can be overcomplicated, but not reduced. And while these were the ponderings of an interaction of a human and a piece of software, it really relates to interactions between systems as well, because if we have multiple consumers of one API, they are directly dependent on that API, which means that every single change to that API will impact all the consumers at the same time. Now, if we move away from the perspective of a consumer, if that consumer consumes multiple APIs from various systems, that means that the complexity grows in that consumer, because now you need to maintain logic of accessing this API, this API, this API, and that basically creates a lot more buildup of code.
Yep.
Because you need to learn about, share the knowledge of all those systems in your system, because you need to understand how they work. Good luck if you're working with SAP R3, which has data models in German and abbreviated. Good luck learning that and putting that in your system, because now you need to consume their API, which was SOAP, not REST, back in the day, if even. So that that's already that level of shared knowledge, right? And then the integration platform, what it does, it moves the complexity of communication away from all those consumers to the integration platform. So it's an abstraction layer or multiple layers of abstraction that safeguards all the consumers from the producers, from the API hosts, producers, whatever, from the upstream systems. So that if the upstream system changes, the change does not have to trickle down to the consumers, because it can be absorbed by the integration platform, because it's a point-to-point relationship between all the providers and all the consumers with the integration platform.
So yeah, I mean, there's a lot of interesting stuff happening there. I think if we're trying to think about what are we trying to explore through a causal loop diagram there, it's not so much that we want to, like, I would try and my instinct is just to focus on, I guess, the aggregate quantities that represents. So like the maybe we have some quantities that represent the like, do you call them like fan out, fan in, or do you use other terms for, like, talked about like multiple consumers of one API, or
Yeah, but that's a specific pattern in from event-driven architecture, right?
Yeah, but it is, but it's also sometimes used for like afferent and efferent coupling, like what depends on you, what do you depend on, this kind of thinking. Trying to think about what I think what you're trying to illustrate is the presence of the integration platform reduces the negative effects of like
it does reduce the effect of afferent and efferent coupling. Yes, that's true. Because I don't really use those terms that often, I just need to a quick refresher on which one is which. Right. So it's for consumers, that's going to be reducing the efferent coupling, because now instead of calling, let's say, 10 different nodes, you call one. And then for producers, that would be the reduction on the afferent coupling, because now they're coupled to through the integration platform. So the integration platform is coupled too, because it's a consumer of an API provided by a system. But no other system is coupled in an afferent way to that system then, right?
So I think one thing that we might be able to do then in illustrating this is it's kind of related to the shared knowledge, right? And the volatility, Because what we're kind of saying is like the integration platform has like it reduces the volatility, and it
And shared
reduces.
knowledge.
What it might also do is allow us to say, so I'm just going to switch to advanced mode, is to actually say, well, it also like reduces these feedback loops, like, and we can just delete them, like we don't have to model everything as like a specific relationship. We say, well, when we have an integration platform, those feedback loops don't exist because the platform reduces the shared knowledge and volatility, and also creates a world where the the feedback from confusion back to increasing shared knowledge doesn't happen, because yes, you might be confused, but you can absorb that into the integration platform rather than increasing the amount of shared knowledge. Potentially, I could be like, I'm making this up really, but it depends on what you're trying to express. But if we see what happens here, if we say, well, actually we have, more integration platform means less volatility, less shared knowledge, reduced coupling, reduced confusion. Maybe that's the story you want to tell. But this doesn't have a feedback loop in it, because I think what we wouldn't be saying is that, increasing confusion doesn't lead to more integration platform or reduced. But what we can say is, because we have this integration platform, we feel comfortable in our model. We used to have this link, and we actually now feel comfortable deleting it, and that can be part of the story.
Okay. Yeah, because what the problem is actually showing this in like two different diagrams. What happens without an integration platform? What happens with an integration platform? Because that's exactly what's there. And there's always plenty to that, because these are completely two different models then, right?
Yeah,
to that extent.
Yeah, so that's actually, I think that's a really good approach, actually, is to create two models and say, if you don't have an integration platform, this is what's going on. We've got these feedback loops that just makes everything worse over time. And by introducing this, we can remove the feedback loops, and actually everything's much smoother. We don't have that continued growth of problems. And this is totally fine. You can show both these diagrams and say, this is the difference between the world we're in and the world we'd like to be in. That's a very reasonable narrative.
I'll send you also in chat here the one where I had the integration platform, basically the same thing but with an integration platform, just to explore this, how I modeled that as a causal effect, not without the feedback. So basically, I implemented that here, that the contract change goes to impacts the integration platform, but not necessarily impacts all the systems. Hence those random cubes on the transition, which is a different, and this was my way of showing this to project managers. What's the benefit of an integration platform? That not every change needs to trickle down, because I tie it to business change. PMs are interested in a governing requirements and changing things, right, in through projects. So not every change in an API must lead to a change in the consumer, because we have that abstraction of an integration platform. Now the question is, while this is causal, what could be the potential feedback loops in this kind of scenario? Because this is basically a visualization of impact.
It is. So I think that this is a very helpful diagram. I would say that it's not strictly following the causal feedback loop sort of premise, and the key to understanding that is to think about what quantities do these represent. So when you say a business change, that's kind of like an event in the world, right? And you're saying, I have a business change which causes this, which causes this. And so if you can draw this diagram, there's nothing wrong with it. It tells the story you want to tell, and it is, it's a nice visualization of it. For it to become a causal loop diagram, we have to think about quantities. And the reason we think about quantities is because as much as they go up, they can also go down. What does a negative business change mean in your visualization of this model? does it like the concept of a negative data model change doesn't really make sense, right? Because
No.
everything's a change. Maybe you're adding a field or removing a field or adding an API or removing an API, it's still a change. So if you can't have a quantity that goes up or down, it's kind of hard to create feedback loops, because
Right.
feedback loops are all about quantities going up, causing other quantities go up, or quantities going up, causing other quantities go down. And that's what allows it to work, because you have to have both the positive effect and negative effect of the pluses and minuses to be able to sort of see the impact of a feedback loop. So that's why in this diagram, I'm focused on everything here is a quantity, except for the integration platform. And I wasn't really clear in my mind what quantity this represents. Like, what does it mean to have less integration platform? And so I think it's really just like a binary. You have one or you don't. And that's why there's no feedback loop. That's why I kind of found myself wanting to move the feedback loop. Whereas in here, or with this original one, they're all quantities. Volatility is a quantity. It can go up or down. Coupling can go up or down. Confusion can go up or down. Shared knowledge can go up or down. They're numbers, quantities that represent like actual, well, they represent, they're models of things that are happening. They might be abstract or sort of ideas of things, but you can imagine there being more or less of them. And that's what allows you to sort of reason about the directional change, because it's all about change. If something's getting more, does that mean something else gets more? If something gets less, does that mean something else gets less? So this kind of diagram that you've created here, this idea of more and less doesn't really exist with some of these things. So that's why I think
it's only more.
It's only more, or even just it's an event, and it's like, it's a thing that happens. What's the consequence? Like, what's the contagion of that thing? And
it's
you can,
the domino effect, basically.
yeah, it's a domino effect. And I don't want to tell you you've done anything wrong, because I think if this served your purpose, if this made the argument you wanted to make, that's great, and that's all you should worry about. But if we're going to talk about causal loops and feedback loops, we do need to think about what's the quantity, and thinking about that quantity is actually part of that whole exercise of like stressing intuition and testing your intuition. What is the thing that's actually going on here? And you can test your intuition further by saying, what happens if I was going up, but what happens if I go down? Does that also make sense? Because if it's correct, it should make sense. You should see it and go, oh yeah, if I have less integration platform, I'm going to have more volatility. That is what I want to say. More, if I have an integration platform, I have less volatility. If I don't have an integration platform, I have volatility. That is what I'm trying to say. So it kind of makes sense.
We can go that way in terms of quantity. Let's think in terms of reusability, composability as architectural characteristics. And for this specifically, we would have to think integration platform being in the API-led architecture being a derivative from service-oriented, right? So in integration platforms, API-led architectural style, you have the channel, you have the composition, and you have the adapter layer. Now, the adapter layer and the composition layer, they provide generic services, either access to data or actual composed services that are orchestrators that fetch data from multiple things, multiple systems. Now, the premise of introducing API-led architecture is that at first it's extremely expensive to build. But the more you build it, the more generic services, the more data services, and the more composed services you have, the cheaper it becomes, because you reuse the existing data services and the existing composed services to provide new business value for new other consumers. So, for example, let's say you have your CRM, which governs your customer domain, subdomain, right? So it's the data master for the customer object. Now, a lot of systems in your ecosystem will require that data object, right, for various purposes. So if we expose that customer as a standardized adapter, as a data service in that adapter, that data service in the adapter can be reused by other systems to get that customer object. Now, the benefit of having the channel layer is that every time the system, any consumer wants a customer, you can exactly trim the response, the actual object, on a need-to-know basis. But you don't have to rebuild the API on the specific domain system every time for each purpose of set of attributes of a consumer, because you have already a generic service for that is standardized. And then you have the channel layer applications and services that expose exactly that subset only to that consumer, right? So then standardization is there in form of the data service, and then customization is then the only thing that needs to be made. The first time you're building it, you build both the channel and the adapter. The second time another consumer wants it, you build only the channel.
Okay. So you
That's
started
quantities.
talking. So the quantities you're interested in there are like the cost of a change, or
yeah. For example, that composability, reusability heavily influences cost of change. Yeah, absolutely.
And so in this kind of modeling, are we thinking then that the like composability and reusability are kind of like at this level, in the sense that like
composability and reusability are kind of, to an extent, analogs of each other in this case.
Okay, well, let's just do composability.
Yeah.
Is it, and then you'd say this is a consequence, like, because we're trying to say it's a consequence of the integration platform, but not directly. Like there's
it's not an integration platform. It's the number of data services, number of composed services that you can reuse. So if at first we have 0, then the cost is high. If we grow the number of data services that we can reuse, that are properly formed, the cost is then lower, because we need to build less to actually make that integration work. If we start deleting those services, because we can always remove those data services, then the cost will ramp up again.
Okay, so we could say number of, let's call it like standardized surfaces. Sometimes the thing I don't like this is if the names get too big, it doesn't cope with it very well. So we just go hash. So number of standardized. So it's not a hashtag; it's actual quantity. The more standardized services, the more composable, which has a negative effect on the cost of change.
Yes.
So we can say more standardized services. Oh, I've got the speed. It's so high. More standard services, more composable, lower cost of change. If we have less services, less composable, higher cost of change. This is kind of the argument you're trying to say. Again, cause and effect. Do you think that there's a feedback loop here? And what would the feedback loop be? Like, would you say maybe that if there is a higher cost of change, then that would cause us to have more or less standardized services? If the cost of change is higher, in a rational system, you would say, actually, that means the higher the cost of the change, then we should be driven to add more standardized services in order to reduce the cost of change. So I think this will end up being a balanced, oh no, this could be a reinforcing, yes. I don't know, why did that? So this is a good question. So now we have our intuition strategy here. We said that when the cost of change went down, that caused the number of standardized services to go down. Oh, that's because we wanted to say the opposite. We wanted to say that when the cost of change goes... interesting. No, what we want is the cost of change goes up. If the cost of change goes up, which would happen if we have less standardized services, then that's going to be pressure to cause us to add more standardized services, right? And if we have more standardized services, that's going to increase the cost of visibility, which is going to reduce the cost of change. And this is where the intuition breaks down, because having the lower cost of change doesn't necessarily mean that we're going to immediately have less standardized services, right? So this is why, and this is sort of what I like about these diagrams, is they force you to confront your intuition. If your intuition was that there is a cause and effect here, then the cause and effect has to go in both directions. Or if we're confident that it doesn't, we can change
Okay.
it. Actually,
I, I,
it's
I can we can add one more note to it. If we have more services, then the cost of change is lower, but the cost of maintaining the integration platform is higher. The operational cost is
okay.
higher.
Yep. This is good. Cost of maintenance.
Yeah. Perhaps change the color to the colors of these.
Yeah, we can make it orange. So more services is a higher cost of maintenance.
Yep.
And a higher cost of maintenance is pressure to have less services.
Potentially. Yeah. And that's especially very visible if you have a specific technology that is pay per use. So, like a model of paying per message or something like that, then there is actually a pressure if the operational costs start growing to lower the number of services,
Yeah.
or
And then
lower the number of chattiness.
yeah. And this is interesting because then we can start to see, well, if we lower the number of services according to this model, that would lower the composability, which would increase the cost of change. So our efforts to manage the cost of maintenance increase the cost of changes, or cost of operations, maybe, let's say, because change is kind of maintenance. And efforts to reduce the cost of change increase the cost of maintenance or operations. So I've actually just temporarily added this one in here, which is another type of link, more advanced one, which is called a convert to positive, which means that we only ever, whether the cost of change goes up or down, we always have an increase. I don't think that's quite what we wanted. It was actually this one. So let's see, if the cost of, let's say we increase the number of standardized services, that increases cost of operations, reduces the cost of the number of standardized services. And what we see is a kind of a balancing loop over time, which will,
Again, not very realistic, because that the drive of operational costs is a bit of a one misguided that leads usually to a killing of an integration platform in that sense. By the way, just for visibility, can you just remove the coupling diagram above, because then it's going to make it a lot more visible if we just drop this one.
Yeah, there we go.
Yeah,
that's better. So I think when I look at this, I mean, you could say over time this is sort of accurate, which is that there's always these pressures in both directions, cost of change and cost of operations, and they cause the number of services to fluctuate over time. Is that what you see over what time frame, maybe?
That's usually over a very long time frame.
Yeah,
especially when the cost of operations is, for example, influenced by an external factor like a change in the licensing model. Then that kind of thing starts happening, because then you start reducing the number of services or simplifying them, or changing technology entirely, which means that you're literally reducing the number of services because you're replatforming entirely, and that doesn't mean that you're recreating all the services on the new platform. And then that again decreases composability, increases cost, and you end up with the need to do more services because the cost is there, unless somebody doesn't understand how that composability reduces cost, and then we have a different problem of knowledge.
Yeah. So I think that I mean, we could model more things into here. One thing I think would be interesting to explore is this link here between cost of change and standardized services. We made the assumption or the intuition that if the cost of change goes up, there's pressure to add more standardized services in order to reduce that cost. And we do see that cost reduction flow through the feedback loop. But it's not necessarily the case that reducing the cost of change would cause us to reduce the number of standardized services. So it's not a bidirectional link. And I think that suggests that actually we should make this a plus symbol, which says increasing the cost of change will increase the number of standardized services, but decreasing the cost of change doesn't decrease the number of standardized services. But because we have this cost of operations balancing act over here, we will sometimes see the number of standardized services decrease because we're going to be like, there is active pressure to decrease the standardized services. And this one we can maybe say is the other way around. It's a minus symbol, because when the cost of operations goes down, that doesn't immediately lead us to increase the number of standardized services. So we've kind of got a loop here, which is putting downward pressure on the number of services, and a loop here that's putting upward pressure on the downward services. This makes more sense. And so we could say here, if we have increase in services, what we see here is actually, we do have a feedback loop, but because these are like gaiters, it's not going to cause a problem. So we say, oh no, here we go. So if we have not enough standardized services, then there's a balancing act here that sort of keeps it stable. It impacts the composability, which impacts the cost of change, which effectively ends up driving pressure to increase the services. The increased services causes an increase to the cost of operations, which drives downward pressure on the number of services. And then we're in a balanced situation now between the cost of change and the cost of operations. So this is a really normal experience that we just had. We started with a simple model. It didn't make sense to us. We tested our intuition. What actually is happening here? We started to find ways to represent what we think is happening. And I think this is kind of maybe saying something useful, which is that the number of these services that you have is a balancing act between the cost of operations and the cost of change. And it sounds like an obvious statement now, but this is a nice way of visualizing it.
Yeah. And then, of course, we have situations where the number of services grows indefinitely. So we end up with thousands of services.
Yeah.
Right. And that and again, this depends on how the architecture is done. It doesn't always support composability if it's misguided, right?
Yeah.
So that's again a different model from this one, because this is where we have this handled. We actually actively pursue composability, and then we're pressured by operation costs to start removing. And it would be perfect if what we're removing are actually dead services. But then that would mean that maybe they're not as costly, etc. Right? And this is all about these ponderings, how these factors influence one another. And it's not exactly easy to observe, because this actually spans between various abstractions and various mental models of different people making different decisions.
Yeah. And this is once again, this is not a prediction engine. It's a tool to help you have the conversation, just as we have just had, to sort of explore what we think is happening. I'm so sorry, Carl. I've just noticed the time. It's almost 9 o'clock. We've been going 2 hours now, so might need to wrap it up soon. I'm sorry.
Yeah, that's fair. We usually wrap up around 2 hours, so that's absolutely a good time to do so. So. So I hope. It's getting quite dark at your place as well.
Yeah, I should, because it was really sunny when we started, and I never got around to turning the lights on.
It's getting a lot. We're getting a lot of light in the evenings now, right? Time change and all. So causal loops, quite interesting. I think that aspect of systems thinking is also quite relevant. So just to reiterate, in terms of books, this book is the one that's very influential in this aspect. Just to start thinking about this causality, those feedback loops, and thinking also in terms of correlation does not mean causation. I think that's one of the things that is really there in that book as well. Still on my reading list, and it's like my reading list is, because of these streams, is only getting longer, which is horrendous.
So there's another one that you might, sorry, not to add more to your reading list, but I think you've already shared the link to my talk, and in the slides there's a link to, as well as Donella Bear's book, Diana Montalian's book, which is called like systems thinking, particularly for software practitioners. So it's an essential guide to nonlinear thinking, and I think that one is very relevant for software developers. So The Donella Meadows book is very general and broad. It looks at systems thinking through many different lenses, social lenses, economical lenses, various things like that. Whereas Diana's book is specifically for software engineers. So I think that's, if anyone who is a software engineer building technical systems that is curious about systems thinking and particularly applied to our context, Diana's book would be worth checking out.
Right, so that's the learning systems thinking from O'Reilly.
Yep, that's the one.
Yeah. Okay. Okay. Right. All right. So to wrap it all up, before we switch off, a few lovely announcements. So next up in about 2 weeks, we're gonna have Vinicius Albano. We're gonna be talking about building communities and how having some sort of a dev community, architecture community can actually influence and change your career. It's probably going to be quite a different talk than the one we had today. And of course, shameless advertisement. If you want to see where we're going to be at in terms of bridging the gap, here's the QR code for upcoming events. You can always go to Bridging the Gap EU.com. Also look it up there. In terms of learning, we're running strategic integration design with DDD Academy from Ardlink. Actually, the first instance of this course done through DDD Academy is starting next Monday. So there's still a chance you can buy a ticket. I think there are still spots available. And of course, if you're new to the live stream and you haven't subscribed yet, please do so. There's a QR code for YouTube. Always fantastic. If you can subscribe, then you can get all the notifications about the upcoming streams. We post those on YouTube as soon as we get them scheduled. So yeah, hopefully more and more subscribers. Someday I'll get the monetization level, right? That said, Chris, thank you so much for doing this dive into causal loops and feedback in systems thinking and explaining why does that even matter and why would we want to actually embrace that kind of visualization and this kind of modeling to defend quality, technical excellence. Because I find it always a challenging conversation with a lot of people, especially people that are not techies. So product owners, business owners, and they force us to cut corners, and that's not always the best thing. And we're always missing the tools to explain why that corner cutting may bite them back later. With these kind of tools, we can actually do that quite nicely, and I believe that this shows a lot more, a lot easier, and conveys the message better that this is a delayed consequence to an extent.
Yeah.
All right.
Excellent. Thank you so much for having me. It was a lovely time. It was great fun.
As always. Yeah. Thank you, and as always, you're welcome to hop on with another topic as soon as we get to schedule one. I think that we had on the list at least one more to chat about. So, if not, I'll drag you in personally at DDD Europe because we'll be probably streaming from the conference as well. So,
wonderful.
Thank you everybody for watching. I believe we still have people watching us at this hour, so that's really cool. And see you in about 2 weeks.